All right, so can you guys see my screen now?
Yes, sir.
All right. Before we start, I would like you guys to grab some coffee. So sa mga kagigising lang, I would like you guys to take your breakfast while having a meeting. So it's better to have a food in your stomach than having nothing, since you have to process uh, this lecture with you. So kailangan merong laman tiyan mo. Anyway, so our topic for today is rectifiers. Okay, so we only have two types of rectifiers. To make it simple, we have half wave and then a full wave rectifier. So under full wave rectifier, we have another two types, which is a four bridge rectifier and then a center tap rectifier. Okay, so without a further delay, let's start. So first, what is rectifier? So a rectifier is an electrical device that converts alternating current, which periodically reverses direction, to direct current, okay, which flows in only one direction. So very straightforward from AC to DC, as you can see on the screen. So the process is known as rectification, since it straightens the direction of current. So this process that we called, okay, from AC to DC is called rectification. Okay, since it straightens the direction. Okay, so simple as that. So the reverse of this one, okay, the reverse of this one is an inverter. Okay, so same, it is also an electronic power device or circuitry that changes a direct current to alternating AC. Okay, so if it's from AC to DC, that's rectification or rectifier. If it's DC to AC, then that's inverter. Okay, so just to make things clear, so those are the two that converts current. Okay, so AC to DC, rectifier. DC to AC, inverter. Okay, but of course our focus for today is rectifier only. So this is just to say that the opposite of rectifier is inverter. All right, so again, we have two types of rectifier. So I wasn't able to include it here. So we have the half wave and then the full wave. And then under full wave, we have the bridge rectifier and then the center tap rectifier. So I will edit this one later since I wasn't able to add the center tap rectifier here. All right, so first is the half wave rectifier. So as you guys may all know, in a full wave rectifier, we have this positive and the negative. But of course, in half wave rectifier, we only accept one. So either the positive or the negative. So if you're going to take a look on this one, okay, we have here a circuit. So we have a voltage source, positive to positive, and then negative to negative. So if you're going to process this one, this will only accept what? Is it positive voltage or a negative voltage? According from this circuit, guys, what kind of current this will accept? Is it positive or negative? Especially this diode, since this is our deciding factor. Yes, Mr. or Miss Golaidan? Negative. It's all right. I thought you're asking a question. Of course, no. Okay, so this will only accept positive current. Okay, so as you can see, our voltage source or our initial input should be positive to positive, and then the other one is negative to negative. Okay, so as you can see, this will only accept positive current or positive voltage. Okay, so this diode will allow to pass through current if it's positive to positive and then negative to negative. Because if this one is negative and then this one is positive, then this one will become reverse bias. Okay, so this one has to be forward bias for us to be able to see that this one will conduct a current. Okay, or this one will allow to pass through a current. So from here, positive to positive, negative to negative. So if that is the case, then it will only allow positive half cycle. Okay, so just abbreviation when it comes to here, what is VM and then what is VO. So VM is our Vmax. Okay, so Vmax is the maximum peak peak value in one half of the secondary winding. So as you may know, in half-wave rectifier, so we use transformers. So we have the primary one winding, and then the secondary winding. So in here, all of the voltage that will pass through the secondary winding will be a DC voltage. So from AC to DC. So in here, the Vmax or the Vm is our peak voltage. Okay. So let's say, okay, let me use the paint. So let's say we have this kind of graph, and then we have, of course, 0 volts here, 1 volt, 2 volts, and then 3 volts. Okay. So as our DC voltage rises, or as our AC voltage rises, okay, it plots, or let's say it rises every 1 volt. So this is 1 volt, this is 2 volts, and then this is the peak voltage, which is 3 volts. So if it reaches that point, then we could see that the V peak, or the Vmax, or the Vm is equal to 3 volts. Okay. So vice versa, if we have this Vm as, let's say, 3 volts per hour positive, the peak inverse voltage is negative 3 volts. So, you just have to uh, put negative sign on it, since in one cycle should be positive 3 and then negative 3. Okay. All right, so moving on. So let's say half-wave rectifier for now is an ideal diode. So when you see ideal diode, if that diode will accept a current, then that will become a forward bias, or simply will become a switch. So in this case, if it's ideal diode, so it's only a closed or open circuit. So of course, if it's conducting a current, then it will become a closed circuit like this one. Okay, so positive to positive, and then negative to negative. So as you can see right here, this one will accept, or this one will conduct a current. So this one will become power bias, or simply a closed circuit. Okay, so if you're going to take a look on this one, this will only accept positive. Okay, so since this one is ideal diode, so whatever is our voltage input will be equal to our voltage output. Okay, so VO is equal to VI. Okay, so VI is input voltage, and then VO is the output voltage. All right, so let's say half-wave rectifier from the t divided by 2, or time divided by 2, to t. So this t here is the cycle. Okay, so 1t is 1 cycle. So of course, t divided by 2 is half of the cycle. So if you're going to take along this one, this is our first half cycle, and then the other one is the another second half cycle, a total of 1 cycle, right? So during the period t halves to t, the polarity of the input signal becomes negative, which causes the diodes to turn off, resulting in an open circuit equivalent across the diode terminals. So before, we only have a positive voltage. So of course, it will go down. It will go down, and it will give us now a negative sign of voltage. So -1, -2, and then -3. -1, -2, and then -3. So our Vm in here is still 3 volts. But now, of course, we have -3 volts. Okay. So as you can see right here, we have +3 and then -3 as our VP. Okay. So during this period, all right. So during this period, to the full cycle, the polarity of the input signal Vi becomes negative. So as you can see at this point already, this one will become negative. And if you're going to take a look on this one, if we have a Vi of negative, okay, so this will not allow to pass through the current, since if our negative Vi is connected to the anode, this one will become reverse bias, or completely open. So as a result, we'll get no current on that particular area. Okay. So for the positive, yes, we have completely, but for the negative, it's 0 volts. Okay. So if you're going to calculate that one, of course, V sub O is equal to I times R. And then if you're going to get the current through that circuit, of course, you'll get 0. Okay. And then times to R. So any number that is multiplied to 0 will become, of course, 0. So as a result, you get 0 volts with this one. All right. So our graph will very depend on our diode. So it's the polarity of the diode. Okay. The same, of course, with the polarity of our voltage source or our voltage input. Okay. So did you guys get the idea so far until this point? From the positive to the negative? Guys, did you get it or
Yes,
no?
sir.
Yes, sir. Yes.
All right. So let me just repeat from this point. Okay. This one will become forward bias since this one will accept a voltage. So positive. But if this one, okay, will become the negative voltage, say this one at this point, this will not accept a current anymore since this one will become a reverse bias. All right. So moving on. So we have here the complete graph when it comes to the voltage input and then voltage output during the half-wave diode rectifier or diode half-wave rectification process. So we have here the full cycle. So we have 2 full cycle. And then if you're going to take a look on this one, of course, this will only accept positive. So positive and then 0 and then positive and then 0. Okay. So if you're going to calculate for the VDC here, okay, so the VDC is equal to 0.318. So where did we get this value? 0.318. All right, so you can use your calculator, okay, and then put here 1 over pi, okay? So 1 over pi is 0.318. So for the first half cycle, okay, if we only have half cycle, that is 1 over pi. But if we have 2 complete cycle, then you should put here 1 over 2 pi. Oops, no, sorry. Not 1 over 2 pi. It's 2 over pi. Okay. So the number above, let's say 1 over pi, okay, 1 dictates the diode that it will pass through. Okay. So in here, as you can see, it only passed through 1 diode, so 1. And then divided by pi. So if it passes through, let's say, 2 diodes, then it will become 2 over pi. But that case, of course, that is now for our full wave rectifier. So also depending on the position, not just if it passes through diodes, then it will become 2 over pi. So depending on the position of the diode. So for the half-wave rectifier, mostly this one is 1 over pi or 0.318. But if it's a full wave rectifier, okay, accepting positive and negative at the same time, then that one will become 2 over pi. So we will discuss on that one on how to use the or how to calculate the VDC a little bit more. So for this half-wave rectifier, you're going to use 0.318, okay, 1 over 5. So I strictly recommend you guys to use 0.318 instead of using the entire value of 1 over pi. All right. So you can check that if you're going to put here in the calculator 1 over 5, we have say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 decimal values. So just use the 3 decimals, okay? The 318, 0.318. So I repeat, when it comes to computing the VDC or the average voltage, okay, just use 0.318 for the half wave and then just use 0.636 for the full wave rectifier. Right? So I think we have here the solution. Oops, none yet. So that's it for the idea for now. So when it comes to getting the V sub O, okay, use this one. Okay, so whatever is the voltage passes through here, then that's our V sub O. And since we don't have, or this one is reverse bias, and you will get 0 volts as V sub O. Right, so moving on, let's say using silicon as a diode. So before, we've considered that as an ideal diode, meaning it could be just a normal switch, open or a closed circuit. But in here, we now have to consider the voltage threshold of the diode. So if you're going to take a look on this one, so you have to cut this part, okay? Since our diode will eat 0.7 volt first before conducting a voltage at this point. So if I will draw the more precise graphs, oops, graph of this one, then we will have this one. So it will not conduct before reaching, or before it will reach the 0.7 volts. So this is I, and then this is our voltage. So it need to eat 0.7 volts first. So 0.7 volts, of course, it has a delay, and then positive. And then another 0.7 volts at this point, and then negative. And then another 0.7 volts, positive. Another 0.7 volts, negative. So bear with my drawing since I'm only using a mouse. Okay, so even in person, even if I'm not using a mouse, my drawing still sucks. So anyway, it needs to consume 0.7 volts first before it will conduct a current. Okay, so that is the idea if we have a voltage threshold of a silicon, or 0.7. Okay, so basically you just have to say wait for, let's see, I don't know, maybe 1 second or 0.30 seconds, and then before it will conduct a current. Okay, so as you can see right here, we now have a voltage threshold. So same idea, you have a positive to positive, negative to negative. It's just that the diode now becomes a silicon diode. Okay, so of course this will only conduct on the positive half cycle, but of course now in getting the V peak, okay, you now have to deduct the voltage threshold. So before, if we have a 3 volts as our V peak, okay, so 1, 2, 3, 1, 2, 3. Okay, so you now have to deduct the 0.7 volts. So our VM, or V peak, now will become 2.3 volts. Okay, so this is our VM. Okay, so same idea, of course, this will not conduct negative at a negative half cycle, since if this is negative and then this is positive, then this will make the diode a reverse bias. Right? So here's a continuation. So while the diode conducts during the rectification process, it generates a DC output that carries a fixed voltage level for the voltage difference. Okay, so before, we only have VO is equal to V sub I if and only if we have an ideal diode. But in here, since the diode now is a silicon diode, so we have to consider the voltage threshold, okay, or the voltage of the diode, which is 0.7 volts. So as always, so VM should be greater than our voltage threshold, okay? Because if not, then meaning you don't have enough voltage input on that part. So you should always have 0.7 volts and above, okay, as your initial voltage, okay? Because or else it will not conduct a current, okay? So meaning the voltage is not enough. It's just partially forward bias. So it should be completely forward bias, okay? So for us to be able to say that it's completely forward bias, then VM should be greater than the voltage threshold, right? And then in computing the VDC, so same idea, it's just that you have to add this one, okay? So before, 0.318 times VM, okay? But right now, you have to consider the voltage threshold, which is minus VT. So VM minus VT, and then multiply it to 0.318. So this is not the exact values, so you're going to use approximate. So VDC is approximately 0.318 times Vm minus Vt. But of course, this is already correct since this is the one that we're going to use. So VDC is equal to 0.318 times Vm minus Vt. Okay. So let's have an example for the half bridge rectifier. So let's have problem number 1. So it says here, consider the diode as an ideal diode. So just by hearing that one, okay, just by learning that the diode is an ideal diode, then there is no voltage threshold on this one. Very easy. Whatever is the voltage input will be our voltage output. Okay. So evaluate the output VO and find out the DC magnitude of the output for the circuit design shown below. So we have here a full cycle, okay, an AC source. We have a 20 volts, positive 20 volts as our V peak, and then negative 20 volts as our V peak for the negative part. So if you're going to take a look on this one, right? So uh, I will leave this one to you. So what is this? Will this circuit accept a positive half cycle or a negative half cycle? What do you guys think? Will this accept a positive or a negative?
Neg- Negative, sir.
So negative. So that's right. So we should have a negative, okay, or a negative AC here, negative to negative, and then positive to positive. So if we have, of course, as always, our voltage input will start at positive. So positive to negative will make it a reverse bias. So if we're going to plot this one, okay, you will see it something like this, right? So for the positive part, it will become 0 volts, and then the only time that it will accept voltage if our AC now is at the negative point, okay, or at the negative cycle. So negative to negative, and then positive to positive. All right. So here's the solution for the problem number 1. So we should have this polarity. Okay, if we have this positive to negative to positive, okay, or either of those two. Okay, you can even have the other way around, so the clockwise, since this one is negative to negative and then the other one is positive to positive. So as usual, this will only accept negative half cycle. Okay, so for the full period of the input AC cycle, the DC output will be VDC 0.318. Of course, just get that formula. So Vm minus Vt. So as you can see in our Vt here, we have 0 since we consider the diode as an ideal diode. So 0 point or negative 0.318 times our Vm is 20 volts minus 0 volts. So 0.318 times 20 will give you negative 6.36. Okay. Oops, I think there's a correction. So this one, at initial part, this one should be negative. Okay. So why negative? Because it is now on the negative half cycle. So the VDC for the negative half cycle will be always negative, and then the VDC for the positive half cycle will be always positive. So at this point, this one should be negative. Okay, or you can change this one into negative. But of course, you have to change this one to positive. So that's quite confusing. So instead, just put the negative here. Okay, as always, for the negative half cycle, and then make this one a positive, and then negative for the voltage threshold. Right, so for this one, our VDC is negative 6.36. Okay, what about our VO? I think I wasn't able to include here the V sub O. What about the V sub O? What is our voltage output on this part? What is the value of our voltage output, guys? All right, so good job, Mr. Pacific. So our V sub O will be 20 volts. So again, in our very first example, if we have an ideal diode, okay, so you don't have a value of voltage threshold, so V sub O is equal to V sub I, okay, which is 20 volts. All right. So let's have example problem number 2. So same. Okay, we have positive 20 volts and a negative 20 volts. So solve for the problem number 1, considering the diode as a silicon. So now we don't have to consider this diode as ideal diode. So this one now has a voltage threshold of 0.7. Okay. So what is our VDC and then what is our V sub O? So I would like you guys to answer this one, okay, and then we'll see if you really understand or really understood the concept of the half-wave rectifier. So just solve for the V sub O and then the VDC. Is there anyone who's trying to answer? What is V sub O and then what is our VDC? For V sub O, you can calculate it manually. Very easy. For VDC, of course, you don't need to use a calculator in that one. All right, so what is your answer, guys? V sub O. What is our V sub O? Kayo dyan. So before, our V sub O is equal to V sub I, right? Which is 20 volts. Okay, but since we now have, right, so someone chat. Very good, Mr. Pacific. So right now, our V sub O now is equal to V sub I minus V sub T. Okay, so you now have to deduct the voltage threshold of the diode, which is 0.7, okay, knowing that the diode is a silicon. So 20 minus 0.7 is 19.3 volts. Okay, so that is our V sub O. And then just by knowing that one, so we can now get our VDC. So negative 0.318 times VM minus VD is of course 19.3. So 0.318 times 19.3, and then you will get negative 6.14 volts. Okay, so here's a step by step, negative 6.318. So our VM or V sub I is 20. So those two are just the same. Okay, initial voltage or the voltage or maximum voltage. So our voltage threshold is 0.7. So 20 minus 0.7 is 19.3. So negative 0.318 times 19.3 volts is negative or approximately negative 6.14 volts. Okay, so that is our V sub O and then V sub or VDC rather. Okay, so the one that is inside here, let me just clarify. This is already your V sub O. Okay, VM minus VD. This is your V sub O. So you can say that VDC is equal to negative 0.318 times V sub O. Okay. So drop in output DC. So as you can see, before we have a voltage of 6.36 for the sample problem number 1 if we consider this ideal diode. And then for the problem number 2, we have 6.14 volts if we will consider this one as a silicon diode. Okay. So 6.36 minus 6.14 is 0.22 volts. And then if you're going to calculate the percentage of that one, the drop in the output DC voltage due to the 0.7 volts factor is around 0.2 volts or approximately 3.5%. Okay. So as always, there's always a difference or there's always a fixed voltage drop when it comes to, considering if it's an ideal or an silicon diode. So there's always a 0.22 volts difference, which is you can neglect it. So you can ignore it actually. So in other cases, if we have 200 volts as voltage input, same. Okay, you will get a 0.22 volts as a difference for those two. Okay, using this one as an ideal diode and then the other one as a silicon diode. Okay, it is actually a fixed value, 0.22 volts, which is 3.5%. All right. So as usual, after the examples, we're going to have a quiz. So don't worry, this one is super easy. Okay, just by looking on that circuit, you already know what is the answer of the piece of O. Well, BDC, you have to use a calculator. So only or find only two missing value. So the V sub O and then the VDC. All right, so we have two numbers here, 1 and then 2. Okay. All right. So moving on, we have the full wave rectification. So from the word itself, full wave rectification, when an AC sinusoidal signal is used as the input for the rectification, the DC output can be improved to 100% level using a full wave. So before we can only gain or we can only have at least half of the wave, so it's only 50% of the level. But for this one, we are now getting the full potential of our AC voltage, okay, which is now using a full wave rectification. So the most well-known and easy process for achieving this is by employing a four diode four diode bridge rectifier network, as shown below. So we have another full wave, which is the center tap, but the most ideal, the most ideal is the four diode bridge rectifier network. Okay, so from the word itself, four diode bridge rectifier. So we have four diodes. Okay, and then the V sub O will be measured on the middle side, okay, or our load resistor. So the same, we have a full wave AC signal, the positive and then the negative. And then we have here your voltage input. Okay, this is where your voltage input will be placed. And then of course, if we have a positive cycle or a clockwise cycle, so your current will pass through here. Okay. So later on, we will discuss on where our current will pass through on those diodes. So for now, we'll stop right here since we now only have 1 minute and 10 seconds. So do you guys have a question so far up to this point?
None, sir.
How about the others?
Answer.
All right. Okay. So those who doesn't have a question, so you may now leave and then just check after 5 to 7 minutes since I need to convert this pre-recorded meeting. Okay. So see you on the part 2.